This is Chapter 4, Earth Materials, Lecture 1. Our goals for this chapter include to illustrate the relationship between rocks, minerals, and atoms, to explore properties of minerals and look at some common minerals, to recognize the utility or use of the periodic table for understanding elements and different types of bonds, and to briefly speak on how we use earth materials in society. Now, with your first discussion, I asked what might interest you about geology. A number of people said, well, collecting rocks is fun. I like the different materials. Perhaps you purchased a mineral kit to help you at least understand in person a little more what we're talking about. That can be good. But we'll look at this specific example from the book. And the point of this is different earth materials are found within a given landscape. Pretty simple, right? So this is near San Diego. Point out in this mountainous range, you have mostly granitic rocks or granite. Further over, this is loose sediment, not rock that is sitting in place in a mountain. And to the north, you can find beautiful tourmaline within the granite itself, so a mineral within the rock. And rocks are made of one or more types of minerals, and minerals are made of elements. Let's look at Yosemite at a few different scales. So first, the landscape. We have a green valley vegetation surrounded by rocky cliffs. The rock is mostly gray in color, and we have a dome structure on the right. If you were to zoom in to the outcrop scale, it looks mostly homogeneous except for these fractures. Going even closer to a hand sample with a Sharpie for scale, you can start to see different minerals within the rock based on color and crystal shape within the rock. If you were to take that rock and grind a slab down to less than 1 millimeter in thickness, put it under a microscope with polarized light, you can see the differences in individual minerals. And this exhibits something called birefringence, where you see it blacked out and clear again as you rotate the sample under polarized light. You can see individual crystals and a little bit of their internal structure at that scale. So what is a mineral? First of all, it's solid. Ice is considered a mineral because it's solid, for one thing, whereas water is not a mineral because it's a liquid. It's got to be naturally occurring. Synthetic crystals are not considered to be minerals. It must be inorganic, so that means the shells of clams and other creatures are not minerals because they are organically created. It has to have an ordered internal structure, and we'll talk a lot more about that in the next coming slides. But the point is, obsidian or volcanic glass is not considered to be a mineral because the atoms within that volcanic glass are arranged randomly. A mineral also has to have a specific chemical composition. So this is salt, which is halite, which is sodium chloride. And no matter how much we break this down to grains and then powder, it's still the same composition, no matter how small. So there's some differences between these two rocks. The top rock has light colored crystals within a gray matrix. This is a crystalline rock. It typically forms from igneous processes, from metamorphism, or from precipitation from hot water, like a hydrothermal rock. The one on the bottom is considered to be clastic. It's composed of pieces or clasts that have been lithified together. It typically forms on the Earth's surface from sediment sourced from sand dunes or rivers. So on the left, we have a crystalline rock versus a clastic rock on the right. They both have more than one type of mineral present. So this is crystalline. You can kind of see that things are interlocking crystals, whereas these are sort of cemented together by finer materials. We'll continue on with the crystalline versus clastic rocks. These have very large crystals and very large clasts. So large we'd consider these to be cobbles. And shapes can differ quite a bit. This is a granite on the left with squared feldspar crystals and smaller minerals as well. This is a breccia. It has rounded limestone clasts within it. Rocks can be layered or not. So crystalline rock here has no layers, another granite. And this sandstone is layered. You can see it on the outcrop scale here. So how do we distinguish one mineral from another? First, you can look at the form of the crystal. The shape of crystals that grow as into minerals, really, is guided by the internal structure of the mineral. We can look at something called cleavage, which you can also think of as breakage. Cleavage is the reflection that a mineral breaks preferentially along one or more sets of cleavage planes. This mineral on the right has no cleavage, but it does have fractures. We call these conchoidal fractures, and that's what quartz has. Color is something we notice first. It's not always the most useful way of identifying a mineral, but it's still part of the process. And then luster. We typically speak in terms of metallic versus non-metallic luster. Luster is the appearance of a mineral caused by how light bounces off of a surface. So metallic luster is something you'd associate with like a chrome look versus non-metallic, which is a dull reflectance of light. There's some tests we can do to help identify minerals. One of them is hardness. Look at the Mohs hardness scale to see how hard or soft a mineral is relative to another. We can look at effervescence, which helps you distinguish a carbonate mineral from something that's, say, a silicate or calcite versus dolomite. Calcite's going to effervesce when a little bit of dilute hydrochloric acid is placed on it. And we can see that here. That's what the bubbles are. You can look at a mineral streak. If you take a ceramic plate, drag the mineral across it, we see a reddish streak. This is actually hematite, known for its reddish streak. It helps you identify the mineral. You can also look at magnetism, take a magnet to it and see if the magnet's drawn to it. Perhaps it's magnetite. Or you can look at the density of the mineral, which relates to specific gravity, to help you identify it. This figure is illustrating that the mineral is at least twice as heavy as water. So we have water on this side and the mineral on this side. So, what controls a crystal's shape? We'll use halite as a good example. And really, we're looking at the internal structure of halite now. You have sodium and chlorine atoms bonded together in the shape of a cube or rectangles. packed together in cubic form, it can look like this. The chlorine atoms are bigger than the sodium atoms. And this is, of course, an orderly arrangement of atoms in a repeating pattern. So halite is one pair of sodium and chlorine atoms. Sodium and chlorine alternate in the crystalline structure no matter what direction you look. How are atoms arranged in a mineral? We can look at a few different ways. These are not the only ways. But you can have a cubic arrangement, a tetrahedron, which is pyramidal, tetra meaning 4, or an octahedron. You have an oppositely pointing 4-sided pyramid joined at the base. Octa, of course, meaning 8. And we'll go back to mineral cleavage, or breakage, really. These sheets represent a direction of cleavage or breakage. First off, we have these brown atoms bonded to blue atoms. They're pretty strong bonds. But the sheets are joined by these gray atoms, and this is a weaker bond. It's going to preferentially break along these weaker gray bonds and cleave into sheets. And this is mica, biotite mica. You can pull it apart like the pages of a book because of that weak bond. You can have a mineral that has bonds with the same strength, and then it will break along 3 sets of planes without passing through an atom. But in other arrangements, a mineral can break in nearly any direction. So it's going to fracture, this is quartz again, with conchoidal fracture, instead of cleave. And this mineral has one cleavage plane direction. So it's one main direction of cleavage cutting through a mineral that grew in 6-sided crystals. It cleaves into sheets. This mineral has 2 cleavage planes. Of course, they'll repeat quite a few times in this direction and in this direction. And they're at right angles to one another. I can show you a video just to show you how this looks. If you were to look around it, this is pyroxene. All right. And these planes aren't the only places where the mineral will break. It can break many, many times in this direction or many times in this direction. We're just showing you the orientation of those cleavage planes. We also have 2 cleavage planes in this, but they're not at right angles. They're non-perpendicular directions of cleavage at 60 degrees and 120 degrees. So 60 degrees here to 120 here. And here we have 3 cleavage planes, as with halite. And in this case, if you were to throw this mineral on the ground, it would break into cubic shapes or rectangles, box-shaped pieces. This mineral also has 3 cleavage planes, but they're not at right angles to one another. There are 3 non-perpendicular directions of cleavage, and you'll see that mineral break into rhombic shapes if you were to throw it on the ground. And we will stop here for today and pick up with the periodic table in the next lecture.